Okay, hello everyone. Hope you are all well. This is Ashwin Shahani here. I am an assistant professor of material science and engineering here at Michigan, if you didn't know that already, and I will be presenting some recent research out of my group. My talk today is titled Tales of the Abnormal Grain Growth in the Presence of Particles. Now, grains actually make up almost all engineering materials, from plastic bags to airplane wings. What sets the grain size in such materials, such polycrystalline aggregates, and how does the aggregate evolve over time? Why should grains grow, such as shown in this schematic illustration? These are some of the guiding questions of my research. Of course, grain growth is only one of our research topics. More broadly, we're focused on understanding the solidification and processing pathways of real materials through in situ and three-dimensional imaging. Our interests span quasicrystals to eutectics, as well as polycrystals, and of course in this presentation I will be speaking more intently about polycrystals. Before I continue further, I want to thank those who actually do the hard work, my very talented team of grad students and postdocs, as you can see in this recent image taken in the pre-COVID era. Okay. In particular, I want to thank Dr. Ning Liu in my group and Jubong Kang, a graduate student, as well as Dr. Nancy Sinabulia at MC Squared for assisting with the X-ray imaging studies. Of course, this research would not have been possible without the collaboration with Carl Zeiss and Ex Novo, nor without funding from the Army Research Office. So I want to thank first and foremost these agencies for their support. I'll start my presentation today with an overview of grain growth, distinguishing between normal and abnormal growth behaviors. I'll also present some foundational knowledge on the driving forces for grain boundary motion in polycrystalline materials. We put all of these theories to work in our imaging studies, and I'll showcase our very unique imaging platform, which combines two different modes of tomographic imaging. The first is X-ray diffraction tomography, and the second is attenuation-based tomography. These results, when fully integrated, allow us to identify the driving forces for grain growth in particle-containing alloys, as I will demonstrate later on. And ultimately, it will allow us to determine the origins of the so-called abnormal grain growth behavior. And lastly, I'll present some outlook for future studies. So first, with some background. Now, anyone who is listening to this presentation has witnessed grain growth, whether you're aware of it or not. If you've blown bubbles, you have most certainly witnessed grain growth. And in fact, the earliest studies of grain growth were quasi-two-dimensional and used soap froths as proxies for inorganic materials because of their transparency, which made it possible to follow the motion of these bubble interfaces as a function of time. This 2D soap froth is representative of a system that is controlled by surface energy or surface tension. And in this case, the law of motion of these boundaries in this soap froth, you can see that the density of boundaries decays over time. All these numbers indicate time steps. This is by Cyril Smith in 1952. And he deduced that the law of motion, it depends on the energy of these boundaries, of these interfaces, and the curvature. In other words, a capillary force. Now, interfaces such as the interface between these soap bubbles cost energy. And of course, the system will want to minimize the interfacial free energy by coarsening the bubbles in this soap froth, decreasing their number density and growing them out, as you can see. Now, such investigations on transparent organic materials allowed us to distinguish two different routes for this coarsening behavior. In the first route, termed normal grain growth, the size of the individual grains is relatively uniform, and you can see that as a function of time, you have a self-similar distribution of grain size, and that is maintained, as you can see, on this grain size distribution. In abnormal grain growth, on the other hand, a few grains grow at a much higher rate than the other grains. You see 2 grains grow out while the rest of the grains remain more or less stagnant. And this results, when plotted as a function of time, a bimodal grain size distribution. And you see that in the end, these 2 grains will consume the matrix of smaller grains, and you end up with a single peak in the grain size distribution at infinitely long times. So that is to say that the grain size distribution in the latter case is not self-similar, and our interests are in identifying the driving forces that govern abnormal grain growth. Why should these 2 particular grains consume the microstructure? What sets them apart? These are questions that we will answer in this presentation. And so eventually, this driving force that is afforded by capillarity will be equal in magnitude to the pinning force that is exerted by the particles or the pores in this material. So these particles exert a drag force, which is called P here, and naturally due to the curvature of the grain boundary, you have some capillary effect, some surface tension that is driving the growth behavior. Eventually, these 2 terms will be equal in magnitude. P here is the exact same Zener-Smith term I introduced on the previous slide. This here is the influence of capillarity. 1 over r is curvature, essentially, and the gamma here is the interfacial free energy. And so you can rearrange this equation, and you can solve for a limiting grain size. So at this particular grain size, the 2 forces are equal and opposite, and grain growth will stagnate. Grain growth will stop because the pinning force exactly balances the driving force from capillarity. So as time progresses, eventually the grain network will asymptotically reach this limiting size, which is proportional to the particle size, which is lowercase r. I suppose I forgot to mention this. The grain size is uppercase r, the particle size is lowercase r, the particle volume fraction is f, and so it's proportional to r over f. At long times, eventually, the system will strike this equilibrium, where the pinning force is balanced by the capillary force, and you achieve this limiting grain size. So this is one way that, that processing engineers, that metallurgists have controlled grain size in material by dispersing these particles. At a given volume fraction and given size, one can attain a given grain size in your material that's proportional to r over f. So the effect of the particles is to slow down and eventually stop further grain growth. This is, of course, our metallurgical intuition. Yet what is perhaps counterintuitive is that abnormal grain growth can still occur in particle-containing systems, in systems that contain a dispersion of second-phase particles. And the reason that this is counterintuitive is that, as I mentioned on the previous slide, one would expect that grains eventually reach a pin configuration where they can no longer move due to capillarity. And so abnormal grain growth is dramatically obvious, as you can see in these micrographs, in transformer steels. These are iron silicon. And you have a few grains in the microstructure that become abnormal, that consume the matrix of smaller grains, and these are so-called Gauss grains. They have a particular orientation. And worth noting is that transformer steels oftentimes have second-phase particles in the form of manganese sulfide or aluminum nitride, which are not pictured here. They're below the resolution of the micrographs, and these may pin some of these matrix grains. And so the underlying question here is, where in this microstructure does abnormal grain growth initiate? And how does it persist to consume the microstructure, right? Why should it continue to grow? And how does it interact with dense regions of high particle density, right? So the underlying question is, how does abnormal grain growth occur in systems that include particles? To this end, we were recently inspired by simulations by Liz Holm and her team from Carnegie Mellon University. These are Monte Carlo Potts simulations. And Liz considered a system with isotropic boundaries, a nearly uniform texture, and random particle locations in a material. And what they observed is that at very, very long times, you have one grain that thermally escapes from its pin configuration. And this is 1 out of 20,000 grains in her three-dimensional MCP simulation. And eventually this abnormal grain attains a size that's much, much larger than the Zener prediction, as you might expect. And at the very end, she ends up with a single crystal. It's important to keep in mind here that her simulations make a number of assumptions, as I mentioned above. Perhaps the biggest is on the particle distribution, that the particles are located randomly in this three-dimensional material. But of course, this is easier to achieve in simulation than in practice. So our goal is to harness in situ and 3D imaging, which is our expertise, to verify this picture and to determine also the influence of the particle locations, the influence of non-randomness in the particle positions. To answer some of these questions, we turn to state-of-the-art experimental probes. Previous efforts in understanding abnormal grain growth in metals have involved so-called quench and look type experiments, wherein a quench material is analyzed post-mortem. It's cut open, it's polished, and its cross-section examined through, say, optical microscopy or even electron backscatter diffraction here to capture the orientations of the grain. So the colors here represent the grain orientations. However, from these destructive probes, it's very challenging to infer or reconstruct the dynamical events that led to abnormal grain growth in the first place. And one could also couple this with a focus ion beam to capture the three-dimensional network, but again, this too is destructive. With that in mind, we have instead turned to X-ray diffraction contrast tomography, which is unique. It is non-destructive, and it allows us to capture the grain locations, the grain sizes, orientations, and morphologies all in 3 dimensions, as you can see in this beautiful picture. And so grain mapping through diffraction contrast tomography previously was only available at a few synchrotron facilities. Among them, the Advanced Photon Source at Argonne National Laboratory outside of Chicago, and the European Synchrotron Radiation Facility in France. But due to competition for beam time, it only allows for a limited number of researchers for a very limited amount of beam time per year. And so there is this limited window of opportunity to conduct experiments at such facilities. To our advantage, we have access to diffraction contrast tomography in the laboratory, which presents its own challenges and opportunities. Perhaps the biggest stumbling block is that, as you might expect, compared to a synchrotron, a laboratory source, which is what you can see on the right, which is our instrument sitting in MC squared. This is a Zeiss X-Radia 520 Versa microscope, offers many orders of magnitude less intensity, less flux. And another challenge is that it has a polychromatic and divergent beam compared to a monochromatic and parallel source at the synchrotron. Nevertheless, my collaborators at Zeiss and Xnovotech were determined to make it work in light of these challenges. And their technique is called Lab DCT. And I put this image here because it gives us X-ray vision into the grain structure from our own laboratory. So how does the technique work? In a typical lab DCT experiment, the source, the sample, and the detector are placed in a symmetric Laue geometry, which means that the sample sits equidistant between the source and the detector. And in between the sample and the source, you also have an aperture to constrict the beam size to a box beam, and you have also a beam stop to block the forward transmitted beam. That way you capture only the diffraction patterns on the detector plane. And so under illumination and during sample rotation, the polycrystallinity of the sample will give rise to these diffraction spots, and actually they're more like streaks, as and when these grains, and one of which is highlighted in red, satisfies the Bragg condition. And so by tracking the motion of these spots as a function of sample rotation, we can reconstruct the grain structure in 3 dimensions. So let's take a look at this geometry in greater detail. And so here I show that same grain in red, and you can see it now magnified in this Laue focusing geometry. Within this grain, there is a set of crystal planes that fulfill the Bragg conditions. That is to say that the diffracting planes act as a lens, focusing the beam to a spot on the detector. On the other hand, you have still beam divergence in the perpendicular direction. So that's coming out of the screen. You still have some divergence, and that's why these spots are actually streaks on the detector plane. And so note here that you have the Bragg condition is fulfilled across the angular span of the grain due to the polychromaticity of the incoming X-ray beam, and this would result in a linear energy gradient that contributes to diffraction. And so this offers several advantages due to the focusing. You have increased signal to noise and substantially less spot overlap on the detector plane. So this is what the output diffraction pattern looks like. This is at MC squared at Michigan. And so here you can see the sample is equidistant between source and detector. We're rotating the sample and we're capturing these spots as a function of time. And we can segment them and back project them onto the sample, and this allows us to retrieve the deep reconstruction. And so the problem of reconstruction is actually an inverse problem in applied math. So one metaphor is, if you consider a ripple pattern on a lake, if you're watching a lake on a rainy day, and you look at this ripple pattern, can you determine its source? In other words, the shape of this droplet of water that splashed out. That is a principle of reconstruction, right? So given some pattern on the detector plane, can you reconstruct the 3-dimensional sample, or in this case, the droplet of water? And so we use the grain mapper 3D algorithm, which I won't go into detail here. That could be its own talk. But suffice it to say that we can use the algorithm to retrieve a grain map. So this shows you the grains in this bulk specimen, and they're colored according to their orientation. To check the fidelity of the lab DCT reconstruction, we can cross-check it against an absorption-based reconstruction. So in this particular sample, we're looking at an aluminum 5 weight % copper sample, where all of the copper segregates to the grain boundaries. And so in this particular absorption reconstruction, we're achieving the maps of the attenuation coefficient. So here, from the absorption reconstruction, we can map out where the copper sits, and if we know where the copper sits, then we can trace out these grains, and we can compare it to the diffraction-based reconstruction to determine, well, how good is the reconstruction of grain shape. So that is to say that the copper constituent acts as a marker or a contrast agent. So if we were to superimpose the absorption and diffraction-based reconstructions, we get this composite map where, again, you can see the copper sits on these grain boundaries. And if we now compute the distance between the where the copper sits and where DCT detects the grain boundaries, we can determine the error in the position of the grain boundaries with respect to the absorption-based data set. And we see that the error is around 3 micrometers based on this test. I should say that this quick check was done when I first started at Michigan 3 years ago. Of course, the technique has progressed. Since then, it's entered a renaissance. And now I think you can achieve even closer reconstructions. And of course now the spatial resolution of DCT is down to around 10 to 20 micrometers. So all of that is to say that if you have a coarse grain material, this is really not a huge deal, this error of 3 micrometers. But if you have a very fine grain material, such as a nanocrystalline material, perhaps you may consider other techniques that might be better suited, such as synchrotron-based high-energy diffraction microscopy, which we also have experience in, but that is not the focus of this presentation. On the X-ray microscope, as I've alluded to, we have other imaging modalities at our fingertips, and one of which is absorption-based tomography. And the technique is very useful in identifying density differences in our sample caused by second phase particles, as we are keenly interested in. And so the absorption tomography experiment is different here. We're focused not on the diffracted beam, but on the forward transmitted beam. You have still a divergent beam of X-rays transmitted through a rotating sample, and you have the transmitted X-rays on the detector are used to reconstruct the sample in 3D. And so the bottom line is that DCT allows us to retrieve the grain structure, while ACT allows us to identify the particle distribution. And so using the two of these techniques in tandem, we can achieve a holistic view of our material, not only the grain boundaries, but also the particles. We focus on an aluminum copper alloy of composition aluminum 3.5 weight% copper. The reason being is that it is known to exhibit abnormal grain growth below the solvis temperature. Below the solvis, the system exists in the form of theta phase intermetallic Al2Cu particles, and you can see them if you look very closely, these little black specks on these micrographs collected by Dennis and Humphreys, and it sits in a matrix of aluminum grains. And you see that if you're below the solvis temperature, right below the solvis temperature, you have this abnormal microstructure, clearly a bimodal distribution of grain sizes, right? A few grains are colossal, and you have several smaller fine grains in the rest of the specimen. We focus on growth due to capillarity, so the sample is fully recrystallized at 400 C for 30 minutes prior to our in situ experiment. And here too, the particles serve as or one can easily identify the particles from the matrix owing to the copper constituent. And so we use absorption tomography to identify the particle positions, and again, diffraction tomography to identify the grain boundaries. We conduct our experiments in a pseudo in situ or an interrupted manner, which means that we anneal the sample, then we image it by DCT, and then we subsequently anneal again. And we continue the cycle until we see one grain in the sample, that one grain being the abnormal candidate. And so what do our results look like at the end of the day? Let me show you the results of our orientation mapping. We image a portion of a very long rod or a wire specimen. And I should have mentioned too that all of the annealing was done below the solvus temperature. So indeed we have a distribution of theta phase particles in a matrix. And so there's sample that exists above and below what we see here, but because of the aperture size, we only image this much material. So one can think of this as an open system, right? You've got grains that might enter the field of view from above or from below. And this is a 3D reconstruction colored according to the grain orientation, according to this standard triangle. So the colors represent the orientations of the grains. And here I'm showing you the results of the isothermal annealing. The numbers that you see in between the reconstructions represent the annealing time increment between the subsequent 3D reconstruction. So this is in minutes, so this is the initial condition, this is after 22 minutes, and then after a subsequent 20 minutes, and so forth. And in the end, you do see that there is one grain, this blue grain, that becomes abnormal and totally consumes the microstructure. In the end, in the diffraction tomography, we see very few and very large reflections corresponding to this blue abnormal grain. So let's look more closely at the initial condition here. As you can see, there's a ton of grains in the microstructure. The sample has no distinct texture, and that due to the grain boundary distribution. If we look at the distribution of grain boundaries, I compare it against a random distribution. The experimental data is more or less random. You do see some preference of low-angle grain boundaries, but by and large, it is nearly random. Grains are about 30 micrometers in size on average, and we capture in the initial state 267 grains, which is truly state-of-the-art. I think in the literature prior to this study, I think the maximum number of grains that were captured in 3D was on the order, or I should say around 100. So this is very good news for us. It affords us very good statistics, as I will show you later on. And so this material is annealed. Below the solvus, we capture the coarsening dynamics of the grain network, and indeed, as a function of time, you see this bimodal distribution at long times, which is consistent with an abnormal microstructure. The question, let me remind you, is to identify which of the grains become abnormal and also to determine what sets it apart. Why should it become abnormal? And to answer this question, it requires us to track individual grains as a function of time, as a function of annealing time. So how do we track grains from one 3D volume to another? This required a substantial computation from my group. And we developed a suite of codes to tackle this very essential task. And our job begins with registration. Registration is a process of aligning two or more volumes taken at different times and from different viewpoints. It's a very important and crucial step in order to extract high-level information. So you have two different data sets here collected at two different time steps, and we want to align these two time steps. This is an alignment problem, and we accomplish this through genetic algorithms. The goal here is to search for the optimal transformation matrix. And here I show you also the grain maps of these two time steps, T1 and T2. And after we do the alignment, we can restore the grain orientations. And you can see that there's good agreement of the grains before and after the anneal segment. So this tells us that the grain orientations don't really change that much. You don't have the influence of grain rotations here in the registered data. So once we find the optimal transformation matrix through a genetic-based approach, which I won't talk about further, we find through this approach a fully affine transformation, which accounts for 6 degrees of freedom in translation and in rotation altogether. And it allows us to identify this intersection volume, this section of the sample that is common to two different time steps. So we do this for all of our time steps, but that isn't all. Of course, there's more to it. We need to also identify the same grain across different time steps. So you've got a network of grains at one time step, a network of different grains at a different time step. And so if you have this grain M, where is it in the next time step? So this is an assignment problem. And so you have two things to consider here. You have the centroid position. So if you have this grain here, obviously by eye you can tell it's not the same as grain M. They have different colors, which mean that they have different orientations, which mean in turn that they have high misorientation. And secondly, you can appreciate that the centroids are different. So it's highly unlikely that this grain is the same as the one at time step t. So we need to consider carefully the centroid position as well as the misorientation across time steps. And so this allows us to formulate a cost function and solve a matching problem where we're matching one grain from one time step to another grain at a subsequent time step, which we accomplish through the Hungarian algorithm, otherwise known as the Kuhn-Munkratz algorithm. And so we solve this combinatorial optimization problem in combinatorial time. An example where we've tracked the individual grain trajectories. I'm showing you here two different grains as an example, one that is growing clearly and one that is more or less stagnant in this three-dimensional polycrystalline aggregate, where again these numbers indicate the time step between these subsequent reconstructions. Of course, there are smaller grains that disappear, and these grains are likely below the detectability limit for laboratory diffraction tomography, which, as I mentioned before, is 10 micrometers. So now that we have tracked grains, given this wealth of grain level data, we can ask ourselves, what is the influence of the initial grain size, which we compute as the equivalent diameter, on a grain's propensity to become abnormal? So here I'm showing the grain size as a function of time for all of the grains in this network. Of course, in the end, you only end up with one grain. All of them would disappear. And so this grain that survives is blue as before, and it enters the field of view at time step t4, which is on the order of 30 minutes or so, if I remember correctly. And so we can correlate the initial grain radius, or the initial grain size, by the volume change of the given grain across time. And you can see here that there's really no trend, that the initial or incipient grain size does not really matter on selecting the abnormal grain. There's no trend detected with respect to the initial grain size. We can also ask ourselves what is the influence of not grain size, but grain topology. In other words, the number of neighbors a grain shares with the other grains. According to Mullins, grains with less than 13 neighbors, which we call F, those are the grains that shrink. And grains with greater than 14 neighbors grow, the mathematical point of zero growth, as you can see here, where this volumetric rate goes to zero, is 13.3. So we can check this. What is the influence of the number of neighbors on the grain's volume change? And here too, you can see there's no real effect of grain topology either. And so these are all, of course, intrinsic factors, grain size, grain topology. There is also, of course, the influence of the theta phase particles, which we also capture. So what is the influence of the external particle cloud? And so here we turn to not the diffraction tomography dataset, but the absorption-based dataset, which shows here the distribution of the theta phase particles. Here we're only showing the centroid positions for clarity. And so you can combine these two data sets to now determine the influence of particle locations on grain growth rates. You can easily see, just by visual inspection, that both the particle locations and the grain size are non-uniform at this particular time step, which is 67 minutes. You see that the particles are clustered over here, and you see one large grain where there's a relatively low density of particles. So with that, we quantified the effect of the particle cloud. And so we plotted here, I don't think this video is playing. Oh well, okay. The nearest neighbor spacing between particles on a histogram. And we see here a very broad distribution of nearest neighbor spacings between particles. Of course, this would indicate that the particle distribution is truly non-uniform and also non-random. If it were uniform, you would expect to see a single spacing between particles and a single peak in this distribution. You also see here that if we were to plot the third order neighbor between particles, so these are the red specks here, the third order nearest neighbors are indicated in the green. You see a nearly bimodal distribution at increasingly high k value at a value of 3, which is qualitatively consistent with this observation of particle-rich regions, so regions of really low spacing, and particle-poor regions, regions of very high spacing, taken up to third order. So clearly the particle dispersion or distribution is non-uniform. And so now we can correlate this, the particle density, where the particle density refers to the number of particles along the grain perimeter as a function of the volumetric growth rate of the given grain. And you see something very interesting here. When the particle density is very, very high, you see that the volumetric growth rate is nearly 0. When the particle density is very low, there's a greater chance that the grains will fluctuate, and they'll either grow or shrink, and this distribution fans out, right? And so this goes against one of the central assumptions of both Zehner's model as well as Liz Holmes' simulation. Both of them assumed a random distribution of particles, which, as we know from our metallurgical intuition, gives to a limiting grain size. But here clearly the distribution of particles is non-uniform. And so with all of these different variables, we really sought to conclusively determine which is most important. We have the influence of grain size, number of neighbors, the influence of particle density, misorientation, crystallographic effects, and so forth. Which one of these factors determines the volumetric growth rate? The statistical tool we use is multiple linear regression, which models a relationship between multiple variables, which I associate with material structure here, to a response variable, which is the evolution of the grain network as codified by a volumetric growth rate. It should be noted that all of this data is collected from our 3D experiments, and as you see here, from the overall regression, or multiple regression, y is the material's evolution, x is a collection of the structural parameters here. You see a positive correlation, and we can break this down further. We can look at the influence of all of these different factors, and with this approach, we show that statistically, the only significant predictor, or the only significant variable for grain growth rate is, in fact, the particle density to a value, to a level of 0.01. And so that is to say that the abnormal grain is selected from a particle-poor region. You have gradients in particle density, and where you have fewer particles, these regions are where the largest grains are found. So you have this very strong correlation due to the particle density. That is to say, again, that the spatial distribution of particles determines the size distribution of grains. To support these results, I should mention too that we conducted dimensional reduction through lasso regularization as well as an ablation study, which we describe in our Acta Materialia papers, and I provide a reference for this later on for those of you who are interested in learning more. So this tells us why the abnormal grain is selected in the first place, yet it does not explain the late stage behavior, namely, how does this abnormal grain grow once it is selected? How and why does it consume the sample volume? And so the question is, why does the abnormal grain persist as it encounters new grain neighborhoods? And so here we formulated this problem on a theoretical basis. Of course, an abnormal grain to grow must have a positive growth rate. It must have a driving force that is greater to 0. This, of course, is true. And secondly, for it to consume its neighbors, it must grow faster than the rest of the grains, as you can see from this latter equation. The grain growth rates, when you take the ratio, must be greater than 0. And so what is done, what Anderson and co-workers did in the 1990s, is they created this mechanism map for grain growth in 2 dimensions. And so here they plotted these 2 equations. One line is due to the first criteria, that the grain growth is positive. The second line is due to the fact that the relative growth rate must be greater than 0. And so when you plot these 2 curves, the inner locus of these 2 curves gives you the characteristic fields for which abnormal grain growth is favored and the conditions where it should persist. Based on the y-axis here is the size of the abnormal grain with respect to the mean grain size, and the pinning strength of the particles, which is what the x-axis represents. So if you were to consider these 2 effects, if you plot them orthogonally, you see that abnormal grain growth is favored when the matrix grains are strongly pinned. In other words, when all of the grains are equal to the limiting grain size, d over dlim is equal to 1. This is when the size advantage goes to a minimum for the abnormal grain. And you can see here that the abnormal grain, for it to persist, it must have a size that is greater than 1.4 times that of the normal grains when the matrix grains are fully pinned. In all of the other regions that you see here, normal grain growth occurs. So that is to say that a grain with this particular size advantage has the potential to outgrow its neighbors in a 2-dimensional system, such as a thin film. One is we have extended this 2-dimensional model to 3 dimensions. Of course, we're considering a bulk specimen at the end of the day. And so we plot here our mechanism map in solid lines. That of other coworkers are in dashed and dot dashed lines. And you see here that in 3 dimensions, there's perhaps a stricter criteria. When grains are fully pinned, an abnormal grain needs to have double the size of the matrix grain in order to grow abnormally, in order to lie in this characteristic field bounded by these 2 curves. So we extended this mechanism map from 2D to 3D. You can see clearly a narrow regime for abnormal grain growth. And what we did was to reconcile our experimental data. We superimposed on this map the grain size data right before abnormal grain growth consumes the sample volume. And so I plot here the normal grains and this abnormal grain, and you see that the abnormal grain is clearly in this region where it should persist to grow and to consume the structure. The normal grains all lie below it. And so the abnormal grain falls into this field where it should persist, while the normal grains are below this region. And so it should persist because the abnormal grain simply has a driving force that is so large that nothing can get in its way. It has a capillary pressure that allows it to keep growing. It's important to recognize the limitations of this approach. The biggest assumption is that the abnormal grain interacts with a mean field distribution of particles, which clearly our work indicates otherwise. It does give us, however, some qualitative intuition, but it doesn't really tell us how the abnormal grain grows through a non-random particle distribution. And so we extended this picture even further to incorporate the influence of a gradient in particle distribution. At least in one dimension, the task can be done. And so we consider here a gradient in a grain size, which is due to a gradient in the local particle density because, as I mentioned earlier, the local particle density determines the local grain size. This is, of course, a Zener-Smith mechanism. And so we have this gradient in grain size in a one-dimensional system. In it, we insert an abnormal grain. Right here, we insert an abnormal grain, and on either side, it will contact grains that are larger and grains that are smaller. And so you have the first three terms here are due to capillary pressures. The last term is due to the influence of the local particle density. And so we can consider the case when the matrix grains are pinned, which allows us to substitute in for Rn, which is a normal grain size in terms of the pin grain size, which is R naught, and identify when an abnormal grain should grow when you have this gradient in grain size. And when we plot the result as a function of this parameter delta here, which tells us how much the distribution departs from randomness, essentially, we see that the size advantage required for abnormal grain growth is relaxed. An abnormal grain doesn't need to have 2 times the size of the normal grains in order to persist. In fact, if you have a gradient in the grain size, and hence in the local particle density, then an abnormal grain can have, say, maybe even 1.7 times the normal grain size and still consume the structure. So the condition is relaxed in the case of a non-random distribution of particles. These insights tell us that indeed the abnormal grain should consume the structure. It doesn't really tell us its pathway. How does it do so? And so here we were greatly inspired by another paper, another very insightful work by Liz Holmes' team at Carnegie Mellon. And according to her group, she determined that abnormal grain growth proceeds through rapid and localized growth events, which give an abnormal grain its irregular shape. So she seeded her simulations with this abnormal grain that grows, and it develops this highly peninsular morphology. And in her simulations, she had both grains that have low mobility as well as grains that have high mobility. The high mobility boundaries are indicated in brown, the low mobility boundaries are indicated in blue. And so what you can see here is where you have these high mobility grain boundaries, the abnormal grain shoots out, and it develops these regions of very high curvature as a result. So you have these localized and rapid growth events that give rise to a highly irregular shape. And so in the interest of relating these simulations to our experiments, we quantified the grain morphology, which offers some clues on its pathway. We quantified shape through the parameter known as convexity, which is the area of the convex hull of a given grain, which is indicated in red here. And we divided it by the area, the surface area of the grain. And so if you have a highly irregular grain shape, you should have a very low convexity value. So this parameter ranges from 0 to 1, where the most irregular shape, such as a fractal, should have very low convexity. A fully compact and equiact structure should have a convexity of 1. And so we tabulated for all of the grains in our microstructure right before abnormal grain growth takes over the distribution of convexity. And you see here that the abnormal grain is at the very tail end of this distribution. It is the most irregular. In fact, you can see these peninsular regions where the abnormal grain shoots out. This is correlated to also the grain size, which is to be expected because the abnormal grain, which eventually takes over the structure, is the one to have also the lowest convexity value. You do see this other outlier here, but this particular grain shares a boundary with the abnormal grain, and so that's why it has such a low convexity value. So you see this very nice correlation as far as shape and size are concerned. Okay, so just to conclude, I hope I have convinced you that 4D imaging, that's imaging done in 3D space and in time, can really provide us with a new vision to study structural transformations, and among them, grain growth. And our work is made possible thanks to this unique and multimodal imaging platform, combining absorption and diffraction-based X-ray tomography, as well as new data science methods to excavate our data and find the patterns within. We find that abnormal grains are located in relatively particle-free regions, and they grow if they have some size advantage. This is confirmed through our analysis of the grain trajectories as a function of time. As they grow, as they develop their size advantage, they also show a very irregular morphology due to these localized growth spurts. Liz Holm, of course, considers regions of high mobility, but in our case, one can consider regions of very low particle density. They are somewhat analogous. That is to say that the local density of particles ultimately determines a grain's propensity to grow abnormally. So what's next? We are using gradients in particles to fabricate single crystals. And this has tremendous benefit in the application space for the processing of materials from semiconductors to superalloys. And maybe next time I'll have more to say on the application side. But for now, with all of that, I hope that the next time you stare into a beer, you contemplate the bubbles. And I hope you can appreciate the richness that is the phenomenon of grain growth, and it's also its ubiquity. Take care, and I hope to see you soon. Of course, if you have any questions, do reach out to me. My email is given, and I would be more than happy to address your questions through email. Have a great rest of your day. And allows us to identify approximately 80% of the grains from one time step to another and track their evolution. So we have now achieved grain level resolution. We can now track the same grain across many different time steps. Of course, 80% is pretty good because, of course, some grains will disappear due to naturally the coarsening process, right? And of course, some grains will, of course, enter the field of view because you have an open system. This is a long rod, which will only illuminate a section of. So 80%, I would say, is pretty good. So here's the growth and shrinkage of grains that you saw on the previous slide depends on the motion of the grain boundaries between them. Assuming that the only driving force is that due to curvature, which is otherwise known as capillarity, von Neumann and Mullins were the first to prove that the growth and shrinkage of a grain in a two-dimensional material, such as, say, a thin film, is directly related to the number of sides that a grain shares with its neighbors. So if you have a grain that has fewer than 6 neighbors, it should encounter a negative driving pressure, and it should recede and eventually disappear in time. If you have a grain that has more than 6 neighbors, then it should grow. And of course, if a grain has exactly 6 neighbors, then it's a state of metastable equilibrium. So this is, of course, in a two-dimensional material such as a thin film. Later on, McPherson and Srolovitz extended this idea to 3 dimensions. They considered bulk materials. And they show that the growth rate is now a function of the triple lines, these edges of the grain network. So this is a grain, it shares these triple lines with the neighbors, and now you sum over all of the triple lines. So n represents a number of triple lines that this grain shares with its neighbors. And E here is the length of the ith triple line of domain D or grain D, and L here is this curly L is the mean width of the grain. And so here, this is an extension of the von Neumann-Mullins criteria for a 3-dimensional network of grains. Of course, the velocity of the grain boundary is dependent on other factors beyond capillarity, such as a dispersion of, say, pores and second-phase particles in a microstructure. The reason for this is that part of the available driving force must be used to bypass the particles. And so note here that you have particles exert a drag force, hence a negative sign, and they tend to pin the grains in their place. So this negative sign indicates that the particles oppose the normal growth behavior, so this is a drag force.